Hi everyone. In this session, we are going to discuss about the next module. So we are going to start with the next module. So that is module 3. So in module 3 you have two topics. One is transformers and another one is domestic wiring. Let's begin with the transformer chapter. And the transformer, so you might have heard about the word called transformer. So what is this transformer? So transformer is a static device, okay. So transformer is a static device by means of which an electrical power, okay. So an electrical power is transformed from one AC circuit, so from one alternating current circuit to other. Okay, so I'll just repeat what is transformer. Transformer is a static device by means of which an electrical power is transformed from one AC circuit to other AC circuit with desired change in voltage and current, but without any changes in the frequency. Remember, so the transformer is a device so which can transfers electrical energy from one AC circuit to another AC circuit without any electrical connection. So without any electrical connection, but with the desired change in voltage and current, but without any changes in the frequency. Here the transformer works on the principle of mutual induction. Okay, so mutual induction, of course it is based on electromagnetic induction, but transformer works on the principle of mutual induction. Here the use of transformers in power transmission is as shown in this figure. Okay, so you can just observe in this figure. So G represents generation. Okay, so where the electrical power can be generated, so this we call it as generation, and further so this has to be transmitted, right? So this has to be transmitted and this part we call it as transmission. Okay, in a short form I write like this, so transmission. And of course during transmission, or so whenever we want to transmit this electrical energy to some other place, so what we need to do, of course the level should be increased for transmission. So why the level should be increased? Because there will be losses especially while transmitting electrical energy, that is during the transmission part. Okay, so there will be a loss. So because of that the level should be increased, for transmission. So you can just observe here, so this is nothing but the transformer and this is how we denote the transformer. Okay, so this is how we denote the transformer. Anyway, so in the next part, so we are going to see the construction and the different parts of the transformer. Okay, so this is how it looks. So we have a transformer and we use a transformer, that is to increase the level especially for transmission, and further so this will be transmitted, and you can just observe initially, so we have some 11 kilovolt and this will be increased to 440 kilovolts. Okay, so this will be increased to 440 kilovolts. So this is for the transmission purpose, and later once it is transmitted, so it has to be reduced again. Okay, that is for the distribution purpose, and here the level decrease for distribution. So here we have another transformer, okay, which transfers electrical energy from one circuit to another circuit without any electrical connection. Okay, so level can be increased, so as I have already indicated, with the desired changes in voltage and current. Okay, the level can be increased or decreased using the transformer, and after this transformer you can just observe, so we have 11 kilovolts. So what happened here? The level is decreased, the voltage level is decreased, that is for the distribution purpose. So finally you can see this is for the distribution, or so this is again for utilization. Distribution means that is for the utilization purpose. So this is how we use the transformer in a power transmission. So now let's see the construction of the transformer. So in the construction of the transformer, so there are two parts. Majorly there are two parts of the transformer. So one is magnetic core, and another one is windings, or we also call it as coils. Okay, so when we come to the construction of the transformer, so it has mainly two parts. One is magnetic core and another one is winding coils. And the magnetic core is either rectangular or square in shape. So remember, the magnetic core is either square or rectangular in shape. So as you can see in this particular figure, and this is the figure of the magnetic core. So now it is divided into two parts. So one is horizontal part and another one is vertical part. Okay, so as you can observe in this particular figure, so it is either a square or in rectangular in shape, and it has two parts. Further it is divided into two parts. One is horizontal part, we call it as yoke, and the vertical part we call it as limb. So the vertical portion, that means the coils are wound. So vertical portion is called limb and horizontal portion we call it as yoke. Okay, so this is nothing but magnetic core. And so here the magnetic core is made up of high grade silicon with steel laminations. Okay, so here these laminations are insulated from each other, so using an insulator like varnish. And so here you can just observe, so they are overlapped to avoid the air gaps. So you can see, so here these are laminated and these are overlapped. Okay, so these laminations are overlapped, that is to avoid the air gaps at the joint. And so generally these joints are in T-shaped or in L-shaped. So as you can see here, so this could be in L-shaped or it could be in T-shaped. And of course, so these are, so the arrangement of these lamination, so arrangement of the lamination is nothing but staggering. So as you can see here, so to avoid the high reluctance, that means high opposition especially at the joints, so alternate layers are stacked. Okay, so you can see here, so alternate layers are stacked here, that is to avoid the air gaps again. So to avoid the air gaps especially at the joints. So this is the construction of the first part, that is magnetic core. And so when we look at the winding, that is the second part of the transformer, windings or the coils. So windings or the coils means, so you can see in this particular figure, so the coils, so this we call it as coils, or we also call it as windings, and which are wound on the vertical portion of the magnetic core. Okay, so the one coil which is wound on the one vertical portion, so this we call it as the primary winding. And similarly the coils or windings which are wound on the other, okay, magnetic core or other part of this magnetic core, that we call it as limb. So this we call it as secondary winding. So in this way the arrangement so could be done for transformer, that is the construction of the transformer. So we have two types, magnetic core and the windings or coils. And these windings are, so you can just observe, so this, for example, if I call it as primary winding and secondary winding, so these two windings should be very close to each other, that is to have the high mutual inductance. Now let's look into the types of the transformer. So you have seen the construction of the transformer. So here, so we have two different parts. So one we call it as magnetic core and another one is windings. So based on the relative arrangement of the magnetic core and the winding, so it has been classified as two types. So one we call it as core type and another one we call it as shell type. Okay, so now we need to have the differences between the core type and the shell type. Okay, so now what are the differences between, as you can see in these two figures, so what are the differences between the core type and the shell type? So in the core type, so and you know this is horizontal portion, and the horizontal portion we call it as yoke and the vertical portion we call it as limb. So based on the relative arrangement of the winding and the magnetic core, so we have two types. And so how we can make the difference, how we can have the differences between these two types? The first difference is here, so we have got two limbs. So in the core type, so we have got two limbs, but in the shell type, so we have three limbs. So this is the first limb, and of course, so we have one more limb called center limb and another limb. So it has got three limbs. And So another difference, the first difference is it has got 2 limbs, but in the second circuit, so we have 3 limbs. And so what is the next difference? So here you can see only one magnetic flux, isn't it? So you can observe here. So we represent the magnetic flux as phi. So here you can see only one magnetic flux, but here we have 2 magnetic fluxes. So one is phi 1 and another one is phi 2. Okay, so another difference is the winding encircles the core here. Okay, the winding. So this is the winding, so which encircles the core in the first part, but here. So here you can see the core encircles the winding. So because since we have core at these 2 parts, so the core encircles the winding. So that is another difference. And since the winding is distributed uniformly in core type, okay, so natural cooling is effective. So I'll just repeat, since here the winding is distributed uniformly over these 2 limbs, okay, natural cooling is effective. But here since the windings are at the center limb, the natural cooling is difficult, so it is not possible in the second case, right? So in the core type, the coils can be removed easily for maintenance. You can just observe the windings or the coils can be easily removed for maintenance, but that is not possible in the shell type. Okay, that is not possible in the shell type. So the coils or windings cannot be removed easily since it exists at the center limb. Core type is preferred for low voltage application, but shell type is preferred for high voltage application. So this is for low voltage application and shell type is for high voltage application. So these are the differences between the core type and shell type. And so this we call it as what? This is the primary winding. So we have represented as P, and this is secondary winding. So similarly you can see the primary winding at this part and the secondary winding. So both primary winding and secondary winding which are wound on the center limb. So these are the differences between the core type and the shell type. So now another important concept, okay, of the transformer is the principle of operation or the working principle of the transformer. So remember, this is one of the important concepts in this particular chapter. So you must learn the working principle of the transformer thoroughly. Okay, so and already you have seen the construction part of the transformer and of course the different types of the transformer. Okay, again this is the type of the core, isn't it? So here, and you can just observe, so these are the lamination, so laminated magnetic core, and so this part we call it as winding or coils. Okay, so there is, you can find one winding here and another winding which is wound on the limb, and you can also see the magnetic flux. And so here the winding or the coil which is wound and which is connected to the voltage source, so you can observe in this figure. So when the winding is connected to the voltage source, so then we call it as primary winding. So this part we call it as primary winding. And similarly the winding which is connected okay, to the load, the winding which is connected, so that is to the load, so then we call it as secondary winding. So here we have primary winding at this part and this we call it as secondary winding. Okay, and with this primary winding with N1 number of turns, so we can have any number of turns here. So let us call this as N1, and similarly we can have any number of turns at the secondary and we call this as N2. So N indicates the number of turns and N1 indicates the number of turns in the primary winding and N2 indicates number of turns in the secondary winding. And again, so based on the number of turns in the windings, so we can have 3 different types of the transformers. So that means N2 is greater than N1, right? So based on the number of turns in the transformer or at the winding level, so we can have 3 different types of the transformer. So that is when N2 is greater than N1, that means number of turns in the secondary winding is greater than number of turns in the primary winding. So this we call it as step up transformer. Okay, step up transformer. So that means which increases the voltage compared to the voltage which we get at the secondary winding, that is at the secondary voltage we call it as. So the secondary voltage will be always greater than primary voltage. So the voltage which we feed at the primary winding we call it as primary voltage, and the voltage which we collect at the secondary winding we call it as secondary voltage. So based on the number of turns, so how the voltage can be increased, that is based on the number of turns. When N2 is greater than N1 we call it as step up transformer. And similarly, so when N1 is greater than N2, or so N2 is less than N1. Okay, so remember, so it could be either N1 greater than N2, or what do we call, so N2 is less than N1. So when the secondary number of turns, okay, number of turns in the secondary is less than the primary, okay, number of turns in the primary, then we call it as what, so step down transformer. Okay, so that means the voltage will be reduced at the secondary. In this case, in the step down transformer, so whenever we want to reduce the voltage, so we can go for step down transformer. And similarly, so what happens when N1 is equal to N2? When N1 is exactly equal to N2, so we call it as isolated. Okay, so there will be no difference in voltage. So that is N1 is exactly equal to N2. Okay, so we call it as isolated. So based on the number of turns in the primary and secondary winding, so it can be categorized as 3. So step up transformer, step down transformer, and the isolated one. And so as you can see here, so we have primary winding and this is secondary winding. And here, so we have voltage source at the primary winding and we have load at the secondary winding. And as I have already explained, so it has, like, all these magnetic cores are laminated one. And here, so we have of course alternating quantity, alternating supply, so we call it as AC supply. And so the duration of this one cycle is 0 to 2 pi, and which we represent it as Tp. Okay, P represents the primary. And similarly you can observe, so we have again sinusoidal. Of course we get similar, the sinusoidal quantity or the alternating quantity at the secondary winding. So that is when we measure the voltage across the load, so we will be getting again AC supply but with the same, okay, TS. So what is the meaning of this, like here Tp is equal to TS, I have written here Tp is equal to TS. As I have already explained, so the transformer which can transfer electrical energy, okay, from one circuit to another circuit, that is without any electrical connection, with the desired change in voltage and current, but without change in frequency. So that means the frequency, of course the frequency is related to the time. Okay, so time, the duration, the time period does not change. Okay, so with the fixed frequency, so we will be getting the same frequency, so both at the primary and at the secondary, and this we call it as secondary voltage and this we call it as primary voltage. So now if we come to the working of this particular transformer, so initially the primary winding gets excited by voltage source. So I'll just repeat, initially the primary winding gets excited by voltage source, okay, by voltage source, and the alternating. So of course when it gets excited by this voltage source, the alternating current flows through the winding. Okay, alternating current I which flows through the winding, and of course when the alternating current flows through the winding, so already I have indicated in the earlier sessions, any current carrying conductor, so okay, will be surrounded by a magnetic flux, okay, magnetic flux. And when the alternating current flows through the winding, so we can have the alternating flux over here, that is phi, the alternating magnetic flux. So when the alternating magnetic flux links to the secondary coil or the secondary winding, okay, so according to Faraday's law, mutually induced EMF gets developed at this level, that is at the secondary coil. So remember, initially the primary winding gets excited by voltage source, and because of this voltage source, alternating current flows through the winding, the primary winding. And since the alternating current flows through the winding, so you can find the magnetic flux over here. And when the magnetic flux completes the path, and of course when it links to the secondary coil or the secondary winding, so what happens? According to Faraday's law, mutually induced EMF gets developed, right? So gets developed, and when if the load is connected over here, so what happens? If the load is connected here, the induced EMF drives a current through the load. So this is how the transformer works, and of course, as I have already indicated, which transfers electrical energy from one part of the circuit or from one point to another point without any electrical connection. And the frequency remains same both at the primary voltage as well as at the secondary voltage. So we have represented Tp is equal to Ts. So this is the working principle of the transformer. So we have term called transformation ratio, and which is denoted as K. Okay, so transformation ratio, and this transformation ratio can be expressed in three forms. So one is voltage ratio, current ratio, and turns ratio. So it is in the form of voltage, current, and the turns. So here transformation ratio, so initially to represent the transformation ratio in the form of voltage, so we express K as E2 by E1. Here, what is E1? E1 is primary EMF and E2 is secondary EMF. So here the voltage ratio, so as I have already indicated, transformation ratio, so can be expressed in the form of voltage and current. So voltage, current, and of course, so we denote it in K. And similarly turns, and similarly in turns. So what is voltage ratio? Voltage ratio is a ratio of secondary EMF to the primary EMF, so E2 by E1, and so which can also be considered as V2 by V1. This is nothing but voltage ratio, and we represent it in K. Similarly, so we have current ratio. So current ratio is nothing but, and we know that, so V1 I1 is equal to, so V2 I2. So what is V2 by V1? So V2 by V1 is equal to I1 by I2. Right? So now the current ratio is nothing but what? It is the ratio of the primary current to the secondary current. So this is current ratio, and we have turns ratio. So turns ratio again. So this is, so, and we know that it is V2, voltage ratio is V2 by, we know that voltage ratio is V2 by V1, and similarly, so this V2, or of course we can also have it as E2 by E1, since the primary EMF is related to what? The number of turns in the primary, and since the secondary EMF is related to number of turns in the secondary, so we can express the turns ratio. As N2 by N1. So the transformation ratio can be expressed in three forms. One is in terms of voltage, current, and turns. So voltage means which is V2 by V1 or E2 by E1, and in the form of current is I1 by I2, and similarly in the form of turns, which is N2 by N1. It is all about the transformation ratio, and which can be represented as K. Thank you.